In this lesson, we're focusing on Domain 2.1. Given a scenario, implement vulnerability scanning methods and concepts. This objective focuses on the practical implementation of vulnerability scanning programs that form the foundation of proactive cybersecurity. Vulnerability scanning is your systematic approach to discovering security weaknesses before attackers find them. This domain teaches you to design and implement scanning strategies that balance comprehensive security assessment with operational requirements and business constraints. We have asset discovery, which forms the foundation of any vulnerability management program. You can't secure what you don't know exists. There are network mapping techniques for this. You have the ICMP ping sweeps, the TCP SYN scanning, the ARP scanning, and the UDP scanning. For ICMP ping sweeps, that's basic host discovery across network ranges. The TCP SYN scanning is identifying live hosts through port responses. ARP scanning is layer 2 discovery for local network segments. And UDP scanning is discovering services that don't respond to TCP probes. Map scan benefits include providing comprehensive inventory of network accessible systems, identifying unauthorized or forgotten devices, and establishing baseline network topology understanding. Once you discover devices, you need to understand what they are and how they function. For operating system identification, you have TCP IP stack fingerprinting, service banner analyses, and behavioral analyses. For TCP IP stack fingerprinting, analyzing protocol implementation differences to identify OS types and versions. Service banner analyses is examining service response to determine software versions. And behavioral analyses is understanding how systems respond to various network probes. For application and service discovery, identifying running services, their versions, and configurations is for understanding the complete attack surface of each discovered system. And device classification is categorizing discovered assets as servers, workstations, network infrastructure, IoT devices, or specialized systems to apply appropriate security policies. And then you have your special considerations for scanning. Vulnerability scanning consumes network bandwidth and system resources, so it requires careful timing coordination. There are the business impact considerations of peak usage periods, batch processing windows, and compliance deadlines. You want to avoid scans during critical business hours. For batch processing windows, you want to coordinate with system backup and maintenance schedules. And for compliance deadlines, ensure scans complete before regulatory reporting requirements. Resource management is balancing scan frequency with network capacity and system performance impact. And then you have operations integration. This involves change management coordination, incident response integration, and maintenance window optimization. For change management coordination, you're aligning vulnerability scans with system changes to avoid false positives from recent modifications. For incident response integration, you're scheduling emergency scans following security incidents or threat intelligence updates. For maintenance window optimization, you're using scheduled downtime for more intensive scanning that might affect system performance. And you have performance impact management, which includes scan intensity configuration, network bandwidth limitations, and system resource monitoring. For scan intensity configuration, this is adjusting scan aggressiveness based on target system capabilities and criticality. You don't want to shut anything down by taking up too much bandwidth with your scanning. You've got network bandwidth limitations, throttling scan traffic to avoid overwhelming network infrastructure or affecting user experience. And system resource monitoring is observing target system performance during scans to prevent operational disruption. That you come to understand what you can do feasibly that way. And then we have sensitivity levels with risk-based scanning, because different systems require different scanning approaches based on their operational sensitivity. There are the high sensitivity systems, the medium sensitivity systems, and the low sensitivity systems. High sensitivity systems are critical production systems that require minimal performance impact and careful scheduling coordination. Medium sensitivity systems are important business systems that can tolerate standard scanning with appropriate timing. And your low sensitivity systems are development and test systems that can handle handle these aggressive scans without any operational concern. For segmentation challenges, network segmentation creates visibility challenges requiring strategic scanner placement, your origin placement there. And with this, we have multiple scanning origins, cross-segment authentication, and firewall coordination. So multiple scanning origins is deploying scanners in different network segments to achieve your comprehensive coverage across those security zones. For cross-segment authentication, there's managing scanning credentials across network boundaries with different authentication requirements. For firewall coordination, this is working with network teams to ensure scanning traffic can reach all necessary network segments. Now we want to think about the regulatory requirements compliance. We have PCI DSS, healthcare, government, and industry specific. PCI DSS requirements include quarterly external vulnerability scanning and annual internal scanning for organizations handling cardholder data. Healthcare compliance, we have HIPAA, HIPAA security requirements for protecting electronic health information systems. And the government standards, FISMA, FISMA, and other federal requirements for vulnerability assessment frequency and documentation. So whenever you see FISMA, think government. Federal. Industry-specific frameworks are sector-specific requirements that may mandate particular scanning approaches or frequencies depending on the industry that you're dealing with. Health versus energy versus manufacturing, etc. Now for scanning approaches and methodologies, you have internal scanning versus external scanning. Your benefits of internal scanning include that it tests security from an insider's perspective, that it identifies lateral movement opportunities, that it assesses internal network segmentation effectiveness, and that it discovers internal-only services and applications. Your external scanning benefits are that it tests security from an attacker's perspective. It identifies internet-facing attack surfaces. It validates perimeter security controls, and it meets your compliance requirements for those external assessments. There is the combined approach, which is that comprehensive vulnerability programs require both internal and external perspectives to identify the complete range of security weaknesses. Here again, we mentioned agent versus agentless scanning. So agent-based scanning advantages are detailed system analyses, persistence monitoring capabilities, and reduced network traffic. The agent-based disadvantages are software deployment overhead and agent management complexity and system resource consumption. And agentless scanning advantages are that there's no software installation required. It works with any network accessible system and it's easier deployment. The disadvantages are limited system visibility, higher network traffic, and credential management challenges, obviously. You've got the hybrid approaches where many organizations use both methods of agent and agentless strategically based on their system types and their management capabilities. Just so you understand what agents are, to make sure you're understanding what this agent versus agentless really means. Agents in vulnerability scanning context are software programs that are installed directly on the target systems, the servers, the workstations, the network devices that perform security assessments within those systems. Agents in local software installation are these small programs that get deployed to each system you want to scan. Think of them like having a security inspector living inside each computer. And there's system level access involved because agents run locally on the target system. They have direct access to the installed software inventories, the system configurations and registry settings, the running processes and services, and the local user accounts and permissions, the file system details and permissions, and the patch levels and update history. It provides persistent monitoring as many agents can run continuously, providing real-time vulnerability monitoring rather than just point-in-time scanning. With agent-based, installation is required. It must deploy and maintain software on every target system. There's deep visibility, though, where you can see inside the system like a local administrator this way, and you get more accurate results with fewer false positives because it has complete system information. And there's management overhead involved because you need to update, maintain, and troubleshoot your agents. And there are system resources used where it consumes CPU, memory, and storage on those target systems. But agentless is your remote assessment, no agent. scanning systems over the network without installing anything, limiting your visibility to only be able to see what's accessible through the network services, and it requires those network credentials if it's going to access systems remotely. And then there's more network traffic generated during the scans, but it's easier to deploy because there's no software installation or maintenance required. Now, when we think about credentialed versus non-credentialed scanning, with credentialed scanning, you have the deep system analyses, the privilege requirements, and the credential management. With deep system analyses, that gives you access to installed software configurations and patch levels. That's how you can deeply analyze the systems. The privilege requirements, administrative access is needed for that comprehensive assessment, and it's important for the credential management to be in place, meaning there must be secure handling and rotation of scanning credentials. Now, non-credential scanning is external perspective, limited visibility, and reduced complexity. Because they have that external perspective, they test these systems as an unauthenticated attacker would see them. They cannot assess internal configurations or installed software because they can't see it. They're not credentialed to see it. They're not authenticated. But there's reduced complexity because you don't have to manage credentials or privilege requirements. Now, passive versus active scanning is important to remember for all these various tests. Passive scanning, traffic analyses, zero system impact, and limited discovery. For traffic analyses, that's monitoring the network traffic for the vulnerability indicators. And there's no direct interaction with the target system, so you've got the zero system impact. But they can only identify vulnerabilities visible in network traffic. There's limited discovery with the passive scanning. It's more stealthy and less potent. Active scanning is direct system testing, comprehensive assessment, and performance impact. This is directly sending probes and sending requests to target systems. It provides more of a comprehensive assessment, being able to identify a wider range of vulnerability types. And because it has performance impact, it might affect system performance during the scanning, taking some of the power away. Then you have your static versus your dynamic analyses. Your static analyses, code review, configuration assessment, and compliance checking. For your code review, you're examining source code or configurations without execution. For your configuration assessment, you're analyzing system settings for security weaknesses. And for compliance checking, you're verifying adherence to security standards and baselines. Dynamic analyses, you've got runtime testing, behavioral analyses, and fuzzing. So with runtime testing, it's testing applications and systems during normal operation. Behavioral analyses, observing system behavior under various conditions. And fuzzing, testing with unexpected or malformed inputs to identify vulnerabilities. Fuzzing often comes up in a lot of these tests. There's reverse engineering and fuzzing. So reverse engineering applications, you've got binary analyses, protocol analyses, and vulnerability research. For binary analyses with reverse engineering applications, you're examining compiled applications for their security flaws. For protocol analyses, you're understanding proprietary communication protocols. And vulnerability research is discovering previously unknown security weaknesses. The fuzzing techniques are input validation, protocol fuzzing, and file format fuzzing. Input validation testing is sending malformed data to identify input handling flaws. So you're giving it something that it does not expect and seeing how it handles it. I'm supposed to enter only a number here, but I'm putting a bunch of different characters in there. What's going to happen? For protocol fuzzing, you're testing network protocols with unexpected message formats. And for file format fuzzing, you're testing applications with malformed file inputs. So we need to cover critical infrastructure and specialized systems. So talked about this, operational technology, OT considerations. Operational technology systems control physical processes, and they require specialized vulnerability assessment approaches. There are unique challenges involved. You've got operational sensitivity. There are often systems that cannot tolerate performance disruption. It would have a bad impact, and they're not capable of handling it. There are often legacy protocols, industrial protocols not designed with security in mind because they're so old. And then air-gapped networks, because these are systems that are isolated from corporate networks and they require special access. They need that extra protection of being air-gapped, though because of that, they're isolated from the corporate networks requiring special access. And you've got safety considerations. Vulnerability scanning must not interfere with safety-critical operations or emergency shutdown systems. ICS, Industrial Control Systems. Manufacturing systems, process control, and building automation. So with manufacturing systems, production line controllers, robotic systems, and quality control equipment are included in this manufacturing systems category. Process control could be chemical processing, power generation, and water treatment systems. And building automation, ICS could be HVAC, that's heating, ventilation, and air conditioning, HVAC, lighting, and security systems in commercial buildings. And then we consider SCADA, supervisory control and data acquisition. Remote monitoring is systems that monitor and control geographically distributed assets. As critical infrastructure with power grids, water distribution, transportation systems, and telecommunications infrastructure. And there are specialized security requirements. SCADA systems often have unique security challenges due to their distributed nature and critical operational requirements. For critical infrastructure scanning coordination, you have the operational team coordination, the safety team integration, and the regulatory compliance. Operational team coordination is working closely with operations teams to understand the system criticality and these acceptable testing windows. For safety system integration, that's understanding how vulnerability scanning might affect safety systems and emergency procedures. And regulatory compliance is meeting sector-specific security requirements while maintaining operational safety and reliability. We want to talk about security baseline scanning and industry frameworks next. For security baseline scanning, you have configuration baseline assessment, drift detection, and compliance monitoring. Configuration baseline assessment is comparing current system configurations against established security standards. Drift detection is identifying systems that have deviated from approved security configurations. And compliance monitoring is continuous assessment of adherence to organizational security policies. For industry framework integration, let's think about PCI DSS again, Payment Card Industry Data Security Standard. We have the quarterly external scanning, the annual internal assessment, and the approved scanning vendor, ASF. For quarterly external scanning, that's required for all organizations that are handling cardholder data. And annual internal assessment is a comprehensive internal vulnerability assessment, are the comprehensive internal vulnerability assessment requirements. ASV, the approved scanning vendor, is external scans must be performed by PCI approved vendors. Then our CIS benchmarks, the Center for Internet Security Benchmarks. We have configuration standards, implementation groups, and assessment tools. The configuration standards are detailed security configuration guidelines for various systems and applications. The implementation groups are tiered approach to implementing controls based on organizational maturity, and the assessment tools are automated tools for evaluating CIS benchmark compliance. And then for OWASP, the Open Web Application Security Project. This is web application testing, the top 10 vulnerabilities and the testing frameworks. For the web application testing, it's specialized methodologies for web application vulnerability assessments. The top 10 vulnerabilities are focus areas for web application security testing, and the testing frameworks are structured approaches to web application security assessment. Now our international standards, the ISO 27000 series, International Organization for Standardization, ISO. The comprehensive framework, risk-based assessment, and continuous improvement. So it's a holistic approach to information security management as a comprehensive framework. For risk-based assessment, it's vulnerability scanning integrated with broader risk management processes. And for continuous improvement, we're looking at regular assessment and improvement of security controls. For our Domain 2.1 test strategy tips, we want to understand implementation questions. Domain 2.1 questions focus on practical implementation decisions rather than tool-specific technical details. These questions test your ability to design appropriate vulnerability scanning strategies. So, question patterns. Which scanning approach is most appropriate for? For this kind of question, you want to consider system criticality and operational sensitivity. Evaluate available access and credential requirements, and think about regulatory compliance needs. Balance comprehensive assessment with practical constraints. Next question pattern. When implementing vulnerability scanning, what should be the first consideration? Asset discovery and inventory typically comes first. Business impact and operational sensitivity are primary concerns. Regulatory requirements may dictate specific approaches, and baseline establishment enables effective ongoing assessment. Next question, which factor would most impact the scanning schedule? So remember, business operations and critical system uptime, regulatory compliance deadlines, network bandwidth, and system performance capacity, and coordination with maintenance and change management. Now, for critical implementation factors for scanning method selection, got system criticality. How important is uninterrupted operation? Access requirements. What level of system access is available? Regulatory mandates. Are there specific compliance requirements? Operational windows. When can scanning occur without business impact? For infrastructure considerations. Network architecture. How does segmentation affect your scanning coverage? System types. Are there specialized systems requiring custom approaches? Performance impact. What level of scanning intensity can your systems tolerate? And security requirements. What level of assessment depth is needed? Your study strategies for domain 2.1, you want to focus on implementation logic. Understand the reasoning behind different scanning approaches rather than memorizing tool-specific procedures. You want to learn compliance requirements, study major regulatory frameworks and their specific vulnerability scanning mandates, like PCI DSS and HIPAA and ISO. Practice scenario analyses. Work through realistic scenarios that require balancing security assessment needs with operational constraints. And then understand system types. Learn the characteristics of different system types and their vulnerability assessment requirements. Some common exam scenarios. We've got scenario type 1, critical infrastructure. Questions about scanning industrial control systems or critical infrastructure. Emphasize operational safety and coordination. Consider specialized protocols and legacy systems, and focus on minimal impact assessment approaches. For scenario type 2, compliance-driven scanning. Questions involving regulatory requirements. Understand specific mandates for different frameworks. Consider documentation and reporting requirements, and balance compliance needs with operational reality. For scenario type 3, network segmentation challenges. Questions about scanning across network boundaries. Consider multiple scanning origins, think about credential and access management, and evaluate coverage gaps and remediation approaches. Some common trap answers. We've got the one-size-fits-all solutions. Avoid answers suggesting the same scanning approach works for all environments. Ignoring operational impact. Don't choose answers that ignore business operations or system performance considerations. Compliance-only thinking. Avoid answers that focus solely on meeting minimum compliance requirements without considering actual security value. And technology-first approach. Don't prioritize technical capabilities over practical implementation constraints. Remember that vulnerability scanning implementation requires balanced, comprehensive security assessment with practical operational constraints. The best scanning programs are sustainable and provide actionable intelligence. Focus on understanding the business justification for scanning decisions. Why choose one approach over another? How do you balance security thoroughness with operational impact? Practice thinking through complete implementation scenarios from initial planning through ongoing operations. Consider asset discovery, method selection, scheduling, compliance, and continuous improvement. Understand that effective vulnerability scanning requires ongoing coordination with multiple organizational teams, including IT operations, compliance, and business stakeholders. Domain 2.1. Test your ability to design and implement vulnerability scanning programs that provide real security value while working within organizational constraints and requirements. Success comes from understanding both the technical and the business aspects of vulnerability assessment implementation.